and we are live. So the last thing we are talking about this stage is the second order linear differential equations. We already started talking about them, and I will use maybe half of this lecture to go through this non-homogeneous version of it. We talked about the homogeneous version, and we are focusing on the ones that have this constant coefficients. If the coefficients are not constants, then the second order linear equation is going to be a bit harder. So we're not going to talk about that. If you want to study this further, you can take courses that have more complicated differential equations. The thing with differential equations often comes with the problem with that is that there is no easy theory that allows you to do even linear differential equations unless they are constant coefficients very easily. So there's a problem related to those even linear ones if they don't have constant coefficients. That for the first order linear differential equation, there is a general solution, and certain subclasses of second order linear differential equations, you can have the similar integrating factors as for the first order ones, but for general, when it's general more complicated, then there isn't a good solution for those. But for constant coefficients, in fact, what happens is that if there's a linear constant coefficient differential equation, be it homogeneous or not, then there always is a possibility to find a solution, so that it may not be easily expressed, but it comes out as one integral of a formula that may be complicated, but the formula can be formed, but not necessarily quite as easy for the more complicated ones. But let's look at this. So I'll jump here. We talked about this. In general, these second order linear differential equations. The thing is that a solution can always be verified very easily as long as you have a function that is easily differentiable. Then just substituting in the formula for your proposed solution, you can check that it satisfies the equation, and that checking of correctness is often far easier than actually finding the solution. And the thing about this is that any linear combination of solutions is always a solution to the homogeneous differential equation, be it whatever kind of homogeneous equation. If you have here on the left things that depend only on the y, and on the right you have 0, well, they may depend on x, but so that there's in each of these the y is a coefficient and it's linear in the left, then a linear combination of two solutions is always a solution to a homogeneous equation like this. Okay, we talked about linear dependence, linear independence, and so forth. That's not going to be a big issue. These are helping concepts, and if you study this stuff further, you of course have to understand the linear dependence and independence of functions, but that is kind of extra material at this point. Just make it easier for you to understand. I tried to justify this the second order equations and finding this this characteristic equation. We talked about this quite a bit, so that if you sorry, if you look at this substitution where your function is of the form some lambda x, e to the some lambda x, then if you find the derivatives of it, the first and the second derivative, and substitute these into this equation, then you get what is called the characteristic polynomial. And then finding the zeros of the characteristic polynomial will in fact give you a solution to this homogeneous equation. And why it has two solutions is because it's a second order differential equation. Then the characteristic equation, or the characteristic polynomial, is a second degree polynomial and usually has two roots. Sometimes it has a single root, which we dub the double root, but even so, the differential equation will happen to have two solution, even if it has a single repeated root. And if it has a repeated root, then in fact, we can find one that a solution where instead of e to the lambda x, you can use x times e to the lambda x. And you can then try it here as a solution. And you notice that if you put them into this equation, then it also satisfies the equation. So this is a way of solving the homogeneous constant coefficient linear second order differential equation. And in fact, this always will result in the solution. So that is you might call a good thing. If you have a complex root, you can actually think of it, the complex, I mean, this would make it easier if we had complex analysis here instead of real analysis. We have the real valued real functions. But you know, if you have complex roots, then you'd have to talk about the complex numbers as well. We haven't talked about the complex numbers all that much, but if you encounter the complex roots, then what comes out are the cosine and the sine functions. You can express them because this e to the something I times something can be expressed in terms of the cosine and sine functions. And then it turns out that you can transform this into this linear combination of the imaginary parts where one is negative and one is positive. And you can in fact applying this Euler formula, you can come up with this situation. You can prove that in fact you can formulate this imaginary exponent part in such a way that you make you can make the imaginary part go away. So even though it has imaginary solutions or complex solutions, then the real parts will always be dependent on the sine and the cosine of x. And then of course, beta x, where beta is the imaginary part of the root. So I didn't use a lot of time to go through this part of the theory, but the summary of the result is here, and I'm not, maybe it's easiest to, this will be easier to understand if you have take a course on differential equations, that we have one that continues from here on, and we can come up with a very, very broad generalization of this when we have a constant coefficient n, you know, of order n, this differential equation, and even more general linear equation systems where that you have expressed these equations with matrices and so forth. So it comes down to finding the eigenvalues of the matrices. If you don't know what that means, it doesn't matter at this point. It's just that for a very complicated system of linear differential equations, as long as it's constant coefficients, then for no matter how complicated the system of that is, you can formulate something that is pretty much the same as this characteristic equation, and you can get all the solutions using that equation. So it's actually pretty neat and works pretty well. There's a well-developed theory from here on. Here are some examples. I put a lot of these in the weekly exercises, these solutions, and then there's the concept of boundary value problem and initial value problem. I didn't talk about the boundary value problem all that much. So the difference, if someone asks the difference between initial value problem and boundary value problem, is that because if you have a higher order differential equation, then you will have more of these unknowns. Like in here, in the generic solution, you have two coefficients, C1 and C2, in these roots for the general solution. And then for this differential equation to be fully characterized, meaning that you know exactly a unique solution, you need 2 points through which this solution needs to go. And the thing is, these points can be given as either talking about the value of the function in 2 points, in which case we're talking about boundary value problem, or you can give it in terms of 1 point in which you know both the function and its derivative, in which case we talk about the initial value problem. And the initial value problem has a unique solution, but the boundary value problem is a little bit more problematic. It may not have a unique solution, it may have several solutions, or it may not have a solution at all. But it might just well have a unique solution, but we don't know in general. So initial value problems are usually far easier. You know the state of the system once you get started, and then you can then express the evolution of the system in terms of whatever the parameter in is x. Sometimes it's time. We take a look at some of the examples where mostly it's time in this system. All right, I'm not going to talk about this example in here. There was the spring mass system, and not going to go through that either. We can talk about that later. Very often the case is when you get this complex solution or imaginary solutions, and what you get is a system whose behavior is periodic. By periodic, we mean that there's the cosine and the sine functions that appear there, and then the solution oscillates. Well, you skip this part. So let's talk about the non-homogeneous version. So in the homogeneous version, the idea is that we have this y prime, and y double prime, and they have coefficients. And in general, they could be dependent on x. We talk mostly about the ones where they don't depend on x, they're just constant coefficients. And then there is the part that doesn't have y in it, it has only x. So this is this Rx in this case. So if that is 0, that Rx, then it's the homogeneous version, which we talked about and which we could solve by solving the characteristic equation. But if there is an Rx there and it's not homogeneous, these solutions are intimately tied. They have a very strong connection, this homogeneous and non-homogeneous solution. And the reason for this being is that if you look at this equation, this homogeneous version of the same equation, if you have a solution for this, then you can freely add any such solution to a solution of this non-homogeneous version, and it doesn't change the right-hand side, because anything you add on the left-hand side will cancel out from the right-hand side if as long as it's 0, right? So in general, if you have some solution, we call it YP, particular solution, that satisfies this equation so that we get the Rx here, and you have a general solution to the complementary equation, you know, really, I like to say the homogeneous version, but sometimes we call it the complementary equation. The equation is complementary in the sense that any perturbation of the solution such that the perturbation, whatever you add to it, is 0, it's actually only complements the solution, meaning that it only makes it different, the solution look different, but the right-hand side remains the same. So in this case, if we have a generic solution, which we know is always of this form, so that we have 2 linearly independent solutions, y1 and y2, for the homogeneous version, then the general solution to this non-homogeneous equation is, in fact, all the variation comes from the variation in this homogeneous part, or the solution to the homogeneous part. Now, this may seem strange because you may find, you know, the particular solution here may be such that, you know, there may be many particular solutions. But the thing is, it's always somehow captured by these, so that the difference between different, if you take two particular solutions and you take their difference, then the difference will always be expressible in terms of this generic solution. So I'm just going to say that if we have for the original, so I'm going to write it like this. Let's say we have the equation, and I'm just going to write it like EQY. So this is the right-hand side. So, sorry, the left-hand side says equation pertaining to y. So this is the differential equation. It contains all the stuff that is y prime, and so. So we say that that's Rx, right? We say that this is the equation, and I don't know. I'm not taking anything about this equation. The only thing I know is that this is linear, and it's Rx, right? So let's say that we have Yp that satisfies it. This is Yp. And let's say we have Yq. Let's say both satisfy equation y is Rx, right? So we have this, both of these, Yp and Yq, both satisfy this equation, the non-homogeneous version. Now, so in other words, we can write that EQ, whatever the equation is, we put this Yp in here, and then it's EQ, Yq is Rx. So we have these two different solutions, and both have this probability. If we substitute them into the equation, we get the same as substituting the Yq to the equation, and that's Rx. So now I use linearity. So I put Yp minus Yq. If I put this Yp minus Yq into this equation, now I use the fact that it's linear. And it's linear, it means that that is equal to the right? So we have this. Because it's linear, we can do this. And that's 0. That's going to be 0 because both are Rx. So if we take the difference here, then in fact, their difference satisfies this equation where this equation is not Rx, but it's 0, right? And hence, it is a solution to the generic equation, you know, the complementary equation, the homogeneous version. All right, it's in this proof as well. So just explaining it a little bit differently. So here are certain solutions that we can try, certain techniques we can try to figure out the particular solution. The thing is, the homogeneous version we can always solve, right? We know how to solve the homogeneous equation. We saw that last week. So we solved the characteristic equation. So we assume that this is constant coefficient differential equation, and there's not going to be any other solutions here, other examples here. So we figure out, one of them is figuring out the so-called undetermined coefficients. So most of these tricks, and I'm not happy with this, this is, and I say tricks because these are really tricks. They're not actual methods of solving them. They are more like, you know, you guess because Rx looks like this, guess the solution and then verify. So this has merit to it. It's not saying that this is wrong or mathematics isn't. Mathematics is full of this thing where you don't have a process by which you can arrive into the solution, but you can look at the solution and then look at the equation, and based on what it looks like, then you can try different solutions and verify them. That's not bad, it's not, but it does give a kind of an idea or a kind of a, it makes you think that this is not really very rigorous stuff. It is rigorous, but it's just that there is no clear solution. So that's why many people don't like differential equations, because they use a lot of this, what people call tricks. So let's look at some of these tricks. Let's not be make too big a problem out of it, but let's just look at it. So one is called the method of undetermined coefficients. So it means that we make what is called an educated guess about the form of the particular solution, and then we put something into this equation, see what comes out, and we may be able to figure out that, okay, this is the solution. So usually when we have this Rx, the non-homogeneous part there, we usually try to find a solution that is similar in form as this Rx, R of x, and not expressible in terms of the general solution. Because if there's a general solution, it's always of the e to something times e to the lambda x, where lambda is the root of the characteristic polynomial. And we want to, in general, what we want to do is we want to try solutions that cannot be expressed in this way, that might result in this R of x. And for instance, if R of x is a polynomial, then it makes sense to try for a polynomial, because what happens to a polynomial when you take if you have an nth degree polynomial and you take its derivative, then what happens is, well, you get a polynomial whose degree is n minus 1, right? Because you take the highest order polynomial, or the highest order x. You know, what is the highest exponent of x? Let's say it's x to the n. You take the derivative of x to the n, what you get is n times x to the n minus 1. So what happens here is that we try, when we have on the right-hand side, the non-homogeneous part is a polynomial, then usually it makes sense to try to find a polynomial of, let's say, the same degree as the right-hand side. Because this 3y here will contain, if it contains the same degree, here it's 1. Then when you differentiate it once, you get a constant, and when you differentiate it twice, you get 0. So in this case, particular solution might, we don't know for sure, but it might have the form ax plus b. Because if we maybe the coefficients may be such that they don't work like this, but they may be. Then we find that its derivative is a, and the second derivative is 0, and we put this into this formula. We put this into the left-hand side formula and try to see if it makes for 3x. And we have two unknowns, ax and b. And just like in the one where we try to transform the rational polynomial function into these partial coefficients, then the same thing we can do here, so that we find just the denominators there, and it's the sum of these 1 over ax plus b's. So in this case, we find that we try to find coefficients for this polynomial in such a way that this equation is satisfied. And if we try, we guess, we cannot be sure whether this works, but we guess that it's something like the first degree polynomial, and that's ax plus b. And we put it into this and solve this, because here 3ax plus 4a plus 3b needs to be 3x. So we get that 3a must be equal to 3, because we have to get the coefficient for x must be 3. And the coefficient, the constant coefficient, which is 4a plus 3b, it must be 0, because there is no constant coefficient on the right-hand side. And this pair of equation gives us a equals 1 and b equals minus 4 over 3. So our particular solution is x minus 4 over 3. And we can double check, well, actually when we solve this equation now, we know if we solved it correctly that this satisfies the equation, but we can also put it back into the equation and try and see that the result should come out at 3x. And it will. And once we've done that, we can verify that, you know, the generic solution here is C1 times e to the minus x plus C2 times e to the minus 3x, because 1 and 3 are minus 1 and minus 3 are the roots of the characteristic polynomial. So a general solution is of this form. And now if we needed to solve the initial value or boundary value problem, then we would use this to determine the C1 and C2. You have to remember that you include the particular solution to the y of x, which then is solved for the initial condition, if you have an initial value problem. Okay, this works very easy. This is easy to understand why this works, because it's first degree polynomial. So, you know, the second degree or the second order differential equation we have very easily happens is that when we take the first derivative, then we get a constant, and second derivative, it becomes a 0. If it's a second degree polynomial, then we need to start with a second degree polynomial. If it's a third degree polynomial, we start with the third degree polynomial. Sometimes what happens is that the coefficients cancel out, and we may have, so that, you know, you start out with the second degree polynomial. There should be a second degree polynomial on the right and on the left, but maybe something happens and some of the terms cancel out, and you won't be able to do that. So you may have to try something else. But usually what you try is the same degree polynomial on the right as on the right, but it may have constants and so forth. Okay. Well, this seems all easy because this kind of polynomial is definitely something that cannot appear in the generic solution, right? You know, you have a generic solution and you cannot have this solution happen there, because in the generic solution, there's only the exponential functions, or if it's complex roots, then it may have the sine and the cosine function appearing, but there is no polynomial there. But what if the right-hand side contains an exponential function? Well, then we make a look. We take a look. We look at the complementary equation, the homogeneous part, and find the generic solution. And if so happens, heaven forbid, that this solution on the right-hand side is not one of these. And it's not in this case, because we got 2 times e to the 3x. So there's no e to the 3x here. We try the particular solution that is simply this something times e to the 3x. Why? Well, the thing is, if we take the derivative of e to the 3x, then its derivative is going to be 3 times e to the 3x. So if we have a something times e to the 3x, then its derivative is something else times e to the 3x. And also its second derivative is something else times e to the 3x. And if we then put this into this particular solution and try this undetermined coefficient attempt, so to speak, this particular solution candidate, and we put it into this equation, we notice that it is in fact satisfied as long as this a is 1/2. So we get this particular solution 1/2 times e to the 3x. Again, you can verify that if you put that into this left-hand side of the equation, then you get 2 times e to the 3x, and that satisfies it. And because this is not something that you can express with this homogeneous solution, then you just add it into the mix. Okay. This exponential candidate is only slightly more made only slightly more complicated when you have the sinus and cosinus functions. Because if you have the sinus and cosinus functions, then what is the derivative of the sinus function? Well, the derivative of the sinus function is the cosine, a cosine, and the derivative of the cosine is the minus sign. So in fact, instead of trying out here just the sine function or the cosine function, you can try a times the sine function plus b times the cosine function. And then you make sure that if you put it into this left-hand side, then the coefficients match the right-hand side. So at this point in time here, I'm going to divide you guys into groups, and I'm going to ask you to do this 7.11. Find the general solution to this. So the process is as follows. 1, find the solution to the homogeneous. I'm going to pause this recording. Well, not yet. So find the solution to the homogeneous equation to generate a candidate, which in this case, because it has sine of t and cosine of t, then I'm going to already tell you that it's going to be a times sine of t plus b times cosine of t. 3, solve a and b. So this is the procedure that you need to do. Find the solution to the homogeneous equation, generate the candidate a sine of t plus b cosine of t, solve for a and b, and 4, express the general solution. All right, now I'm going to pause the recording. So what we got was the solution, particular solution was sine of t plus cosine of t. Yeah. All right, let's carry on. Here are some of the, here's really a table with no need to go through all these possible situations. Here is a list of key methods that you can try, that's key forms that you can try. Initial guess for the particular solutions should probably be, if it's a polynomial, it's a polynomial of the same order as the R of x. If it contains sinus and cosinus functions, then simply a linear combination of sine and cosine functions. Again, remember, if it's just cosine on the right side or just sine on the right hand side, it's usually necessary to include in your guess or in your initial candidate both the sine and the cosine, because when you take their derivatives, both appear, even if they are supposed to cancel out. Then there are these combinations where you have exponential functions and sine and cosine. If you have a polynomial times an exponential function, there is a, I hope this drilling sound is not coming through. There's someone is drilling somewhere in this building. So here are some of the initial guesses for that. The thing is, sometimes the problem arises that if we guess a particular solution, then we may run into this problem that, that the particular solution is in fact, our attempted particular solution is in fact one of the solutions to the homogeneous equation. And if this is the case, then obviously it cannot work, because if we try that out, so here's an example. One example in which we have a linear constant coefficient equation, and then we have on the right hand side there is 3 times e to the minus 2x. Upon closer inspection, we notice that in fact this 3 times e to the minus 2x is in fact one of the complementary solutions, or the solutions to the homogeneous equation, and in which case it has no chance of ever being a solution, a particular solution, because if you put that function on the left-hand side, then it just cancels out, because it is a solution to the homogeneous equation. Then one way to do this is to include additional terms, just like we have in the case of double root. If we have a double root and we have this e to the something x, and we have a double root, let's say a, and we have e to the ax, then we add also x times e to the ax into the mix. And that has the capacity to generate this solution. So in this case, including a times x times e to the 2x, because if we find the derivative of this, then there will appear two terms. One where there is e to the 2x, and we know that's going to cancel out, but then there is the one where there's x times e to the minus 2x, and then that has the capacity to have these terms cancel out in such a way that in fact this e to the minus 2x may be left on the right hand side. So in this case, we try a solution where there is the particular solution attempted, a particular solution, instead of having e to the minus 2x, it's something times x times e to the minus 2x. And we try this out into the particular equation, and then as luck would have it, this a times e to the minus 2x is left on the left-hand side, and we can solve this for a, and we said get that a equals 3, so we get this particular solution. And we get the general solution here as well. So you have to make sure that your particular solution attempt or the initial guess is not something that appears in the equation, homogeneous solution to the equation. And if so, if it so happens that it is something that appears in the solutions to the homogeneous equation, then one thing to try is to take that guess that you might need, multiply that by x. Because if you multiply that by x, then because of the way the derivatives product rule works, then you end up with x times yp plus the derivative of yp times x. So the derivative of yp times x plus yp. And then that has the capacity to generate that kind of solution. It doesn't always work even so, but you can try. And most of the cases it will work. So here are some of these non-homogeneous equations. I'm going to discuss this slightly less later. There is also something called the variation of parameters. I'm not going to go into this variation of parameters. This applies when your right-hand side has more complicated functions like logarithms or something like this. It's not a nice explanation there. Undetermined coefficients doesn't really work on those kind of functions. And there are all these things like the Kramer rules and stuff. I'm not going to go through this. This goes to a pretty advanced tomfoolery, so to speak. So I don't think it makes sense for me to assume that you will be able to do this. So yeah, I'm going to skip this these applications. I'm going to show you this just very quickly. I put in this week's exercise one that talks about this. Let's see, this RLC circuit. Let's see here. Let's see, where is it? It's in here. The RLC circuit, we have the series RLC circuit, and it's modeling. So I gave a set of particular values. Oh, I made a small blunder because I wrote here C instead of 1 over C. I'll fix that. Don't do that yet, I'll fix that. So the idea of this is that the external voltage must all be consumed whilst in this route, and the voltage over the capacitor. I forgot. I made a small blunder in that. I'll fix it. It's 1 over C times Q, where Q is the accumulated charge. So that's in fact the charge, meaning it's the net charge that has flown through this circuit. So I express this. This can be expressed as an integral of the current from 0 to t. I did it slightly differently. So here's an example on how to solve it, how to solve this. And here it was given that the external voltage was given as a constant 300 volts. I gave a simpler version, and I did it in parts there, slightly different numbers there. I'm going to change that a little bit because there was a slight error in that. So if you downloaded the weekly exercise, I accidentally put here C instead of 1 over C, which was just I don't know why I made this blunder, but I'll make sure that that's fixed today before I do anything else after this lecture. Okay. But basically, just a very quick recap, what I expect you guys to be able to do here in this case, with respect to these differential equations, I would expect you guys to be able to, and just have a, so here, I want you guys to realize that what this week's exercise pretty much covers the things that I would like you to be able to understand. Separable equations, meaning you put the y's and the x's on opposite side of the formula, and then you just integrate. That's easy. The logistic equation had a particular kind of solution. It's usually useful for things like population dynamics. There are other situations where it's then first order linear equations, which had this solution that you can just have the integrating factor, and then the second order linear differential equation that has constant coefficients. And those are the only ones that I would expect you guys to be able to handle in this course. So not too much, I hope. That forms quite a bit of this thing, but why this is a little bit relatively short time of period when we cover these. There's not much stuff there. And you need to be able to apply the things that we talked about. You need to be able to find the derivatives of these candidates. That's why the derivative thing was, you need that and the derivative rules. You need to be able to, in the case of the separable equation, you need to be able to find integrals of relatively complicated, but not too complicated, but somewhat complicated functions. And then, just apply in certain models, apply these ready-made rules, which you can then look up in the book. You don't have to remember them all. So I hope this covers that, so that we can move on to the next topic at hand, the last topic really, if you think about it, and that would be these sequences and series. So in an ideal world, I would have talked about the sequences and series before we started talking about the derivatives and so forth. The reason being that the series is convergence and limit is actually something that can be taken as the fundamental thing, and then apply the function's limit at a point in such a way that you define it using these limits of sequences. So this Koch snowflake, it has nothing to do with politics, by the way. I mean, for some reason, Americans use this snowflake thing, and we don't mean that. The so-called Koch snowflake means is very easily generated by this. It's easy to understand, but it's mathematically a bit hard to grasp using some kind of equations or anything. But speaking in terms of how the Koch snowflake is done, is you start with a triangle, and then iteratively on each iteration, each step of the way, you take all the straight edges of whatever you are dealing with at that time, divide those edges into 3 parts, and then bulge out the middle part into such that it becomes, its length is doubled. So every 3, it's a 3, you divide this one side into 3 pieces, the middle 3/3 is doubled so that it kind of protrudes out and makes this into this kind of an edge or a star. And then every straight line here, you do the same thing in the next episode, right? You do it, it becomes like this. So the triangle becomes a star, the star becomes this kind of like snowflake, and it starts making this weirder and weirder looking, you know, the closer you would zoom into this, then the weirder it would look. And if you do this to infinity, I mean, obviously, if you take the limit of this process, if you were to be able to do this to infinity, then what would you get? Now, well, the cos snowflake is a little bit weird construction, and we're not going to talk about it, but it's a nice concept in the sense that it has a finite area, because you notice that this whole thing will always fit inside this certain polygon that you can draw over this, and it doesn't ever you know, protrude outside that. But the length of this diameter line approaches infinity because it becomes bigger and bigger. Well, we can talk about that later, but it's not really that. We'll talk about these sequences now. So what is a sequence? A sequence is basically consecutive numbers, A1, A2, A3, and so forth. And we think of this as a list that continues into infinity, in the sense that you have an infinite number of these. It is possible that from some number n, some index n forward, it's just one same number. I mean, a sequence where it's just 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and everything is 1. That's definitely a sequence. Often we use this put it in these braces, and sometimes we say that the index n ranges from 1 to infinity, or sometimes simply just put it in braces, an, and that denotes a sequence. So here's one, you know, the sequence which is determined by, very often the case is that, well, not very often, but in these examples, very often the case is just that given an n, we actually have a function that gives you the nth element in this sequence. Like in this case, example 2, 4, 8, 16, 32, well, the next one might be 31, you know, we don't know what the next one is, but let's say someone tells us that this is in fact a sequence such that the nth element will be 2 to the power of n. Then we can express this in such a way that even though this is like the index notation an, we don't know what that an is necessarily. Here it's like a function notation. So this is 2 to the n, where n ranges from 1 to infinity. So this is a sequence of all the powers of 2. There are different ways of expressing these equations. One way to express this sequence is to express this recursively as a recurrence relation, meaning that we express that an is expressed in such a way that an is double that of an minus 1. So if you've done some of these simplistic IQ tests that claim to be IQ tests, they're not really very good IQ tests, because there's a great skill component there that can be easily acquired. If you've done these online IQ tests, then very often the case is that there is a simple recurrence relation that you can spot very easily, such that the next one is always 2 times the previous one plus 1, or maybe it's the previous one plus 3, or maybe it's something like this. And you know, you are asked what comes next. And the idea is for you to be able to spot this. And the human mind is weird in that that actually this recurrence relation, or this recurrence equation, you know, expressing the next in terms of the previous, is very often much easier to come up with than an explicit rule. I mean, if you think about how you look at these sequences, very often you come up with something like this. So sadly, we don't have all that much time here to talk about these sequences and how they can be easily defined. So not going to spend too much time on this recurrence relation. I just mentioned that this is one way to look at these sequences, and it's in fact a whole field field of study, you know, what kind of sequences can you in fact express using recurrence equations, and that's actually a really powerful tool. But I digress. I don't want to talk about that too much. The indices do not have to start from n equal 1, although sometimes they start from 0, sometimes they may start from even 2 or something like this, but it doesn't really matter. If nothing else is mentioned, we assume that the first one is 1 or 0, depending on the context. And there are all these kind of things like plotting the graphs and so forth. And, you know, when you have a recurrence relation, then you can look at this formulate the next one in the sequence and so forth. Now, not going to go into here too greatly. Usually we say that this sequence is arithmetic if it can be expressed in terms of recurrence, where you only add something to the previous one, and then we say that usually that it's geometric if it's the previous one multiplied by something. In other words, the arithmetic sequences are usually linear or affine function, affine meaning it's linear plus constant functions of n, and the geometric ones are usually exponential functions of n. So arithmetic, linear, or you know, if you allow here to be some polynomial is added, sometimes you call that also arithmetic, not always, but. So these sequences can be classified. We're not going to be using too much time on this. Also, we're not going to be spending a lot of time on this finding explicit formulas. If you come up with there's a recurrence, then sometimes you can come up with this explicit equations for those. Not always. I mean, sometimes if you come up with a recurrence, then the explicit equation for that is not easily forthcoming. There is a whole book. I'm actually going to recommend it to anyone who is interested in these sequences and series and so forth. A book called Concrete Mathematics by, so I'm going to write it here. If you are interested in this stuff, I don't think it is in the curriculum. I think it was Patashnik. I don't remember how it's Donald Knuth and some guy. I think it was written Patashnik. I'm not sure exactly how it's written, but this book, it's actually I recommend it if you are interested in sequences and so forth. It's a very good read, very concrete. When this is concrete mathematics, very concrete in the sense that it's got a lot of these sequences can be justified in a certain way, a bit contrived though. I would call it contrived concrete mathematics, because I mean some of these are really strange, but it does broaden your mind a little bit if you are not familiar a lot with these sequences. So I really, if you have time or energy or you are interested, then look at this book. Not, of course, this course will not. I'm not going to ask any questions that would require you to do that, and it's of course out of this scope of this course. But I'm just saying that that's one thing that you might be interested in if you find this fascinating. So, if you define these by recurrence relations, then very often the case is that there is a way to come up with an explicit equation for that. If you can do it in the following way. This is pretty much the same way as Knuth and Patashnik recommend doing it, and you can then notice that there is a general way when you write these terms out in terms of the initial value and the values that appear in this recurrence. So, for instance, in general, this kind of a recurrence, which is a geometric recurrence, because you're multiplying the previous one with something, then it starts out with the initial one times an exponential function of whatever it is that is multiplying that. That's usually what happens when you have a recurrence that is geometric. And when I say usually, I mean that's exactly what happens actually. So yeah, this may be harder when you are adding something that depends on n. It may be harder if you're multiplying with something that depends on n. It may be harder. You may not be able to come up with this. The thing is that if you come up, this can be solved in a similar way as we can solve differential equations by guessing the answer and then checking that that answer satisfies the equation, like with the particular solution of second order differential equation. In the same way, if you have a recurrence relation, then very easily you prove it actually by an induction. You show that when you put n equal 1, you get the first one here. And then if you show that if this is in fact true for n minus 1, and then you apply the recurrence, then you get this for n, for n. And that's actually the recurrence. You can think of, I mean, if you're familiar with inductive proofs, then you can think of inductive proofs working on, I mean, inductive proofs are usually things that you prove properties of recurrences fairly easily. And they come up like with this duality. So you use a recurrence to define something, and you use induction to prove that it satisfies that recurrence. So the two are like friends in some sense. Okay, I urge you to go through these things. The thing that I'm really interested in talking to you about today, and in general about these sequences. By the way, I gotta ask, is that drilling sound coming through? Is it
like a bit, but it doesn't affect anything?
It doesn't bother. Okay, good.
No.
It's bothering me a little bit, but it's not very loud, so I'm hoping that it doesn't cloud my, go over my voice, so you can still hear and get. All right. Good. So what we're really interested, what I'm really interested in, and what I want to talk about, what we want to apply these sequences into is the concept of a limit of a sequence. So in these recurrences that we mentioned, many of them, like the arithmetic and geometric, well, not always geometric, but arithmetic usually, what it comes down to is that when you go further into the sequence, then sometimes, the numbers just keep on growing. And as n goes to infinity, you get larger and larger values all the way to infinity. So we kind of say that, okay, the limit of the sequence doesn't exist, or the sequence, we say that it diverges, meaning that it goes to infinity, or doesn't go, there is no limit in which it approaches if n approaches infinity. If the number approaches infinity as n approaches infinity. But then there are sequences like this one where we got this explicit solution that it's 1 minus 1/2 to the power of n. Then in fact, if you look at what happens when n approaches infinity, then this approaches 1, because this 1/2 to the power of n goes towards 0, so 1 minus that goes towards 1. So that limit has that sequence has a limit. Also, see this minus 1 to the power of n doesn't have a limit. It doesn't grow, but it doesn't have a limit. And we would like to define what the limit means. It doesn't have a limit because there's no single value which it approaches. So you already have this idea or concept of limit from functions. The limit of a function when the parameter approaches some number. So I would have loved for us to first start with this concept of a limit of a sequence, and then use that to define the limit of function at a point. But if we talk about the limit of a sequence, then we can't really do that easily with the limit of a function characterization, because the function, the way it approaches wasn't really defined in that way. But the intuition can be thought of this way, so that you can think of this as us having a sequence of numbers when we are looking at the limit of a function, and we're taking numbers that are closer and closer to that value that we are looking at. So there's a sequence of x's which goes towards the point at which we are evaluating the function. And then there's a value of the function which approaches, hopefully, some value whilst we go closer and closer to the limit point. And inside here, in this definition, there would be a sequence. So we're kind of working backwards here to define the limit of a sequence now, instead of defining the limit of a sequence and then applying it to find the limit of a function. So there's one example here, -1 to the power of n over n, and that approaches 0, even though it oscillates between negatives and positives, but you know, it goes towards 0 as we go towards infinity. Here they're, I wouldn't say plotted, but yes, plotted some of these sequences and the points. The definition here, what is the definition? We say that we have a sequence an. Now this means that it's an infinite sequence of numbers. And we say that this sequence has a limit. And now it's, I don't know why it's written like this. It says, say that it's convergent sequence and L is the limit, and we write this if it gets closer and closer to this finite number L. But that's not mathematics. That's you know, it's not mathematics. That's fairy tales. That's storytelling. We're not here to tell stories. We're here to do math. Obviously, I mean, obviously, I'm joking here, but you know, the thing is, why would we call this definition? That's not a definition. That's an intuition. They should call this intuition and not definition, which is, you know. So we say that a sequence converges to a real number L if for all epsilon, and notice how we are using the epsilon like we had the epsilon delta, there exists an integer n such that whenever we take an index n greater than this capital N, then all the numbers in that sequence after that are closer to L than epsilon. So the limit means that no matter where you put, let's say here is the value of the proposed limit. So no matter how small a bounds you put here, then you know there are only finitely many number of points that fall outside this threshold. Here, if it's L plus epsilon, L minus epsilon, then there is a point somewhere in here. Let's say this is your capital N here. I'm going to draw this annotation 2. So this capital N here, this is the limit point, right? Oh, well, sorry, the line. Anything on that right, everything is between these two lines. There may be something on the left-hand side that where they are above and below, above this upper line, below this lower line. But on the right-hand side of this, everything is between these two lines. And the limit is in fact this blue line here. If it doesn't matter where you put these, then there is always somewhere over there on the right, there is a point after which all the numbers are between those two bars. And it doesn't matter how close you put those two bars together, it will always be, there is always going to be a point after which everything is between those two lines. Then we say that it converges to that limit. All right? So this is something that may require a little bit of thinking, but this is in fact easier to think in terms of this. And I hope you understand now that it's simply because of the book presents them in this order that we did it, so that we first talked about the epsilon delta in the functions and not the sequence. The sequence is far easier to understand, in my opinion, so that, you know, someone gives me a list of numbers and I say that this list of numbers has a limit. If, you know, if I no matter how small a threshold around that limit I put, then I can cut the sequence somewhere short, and there's only a finite beginning part where it may go outside this, and everything after that goes inside these limits, this epsilon plus epsilon minus epsilon. So if we can't find such limits, if there is some epsilon or you know, there is no such L such that this approaches that like this, then we say that the function, sorry, not the function, the sequence converges, diverges. So in this case, it converges, but if it does not converge, it is divergent. It's diverges. And divergence here has nothing to do with that young people's book and movie series. My kids love that. Divergent, but you know, this has nothing to do with that. So don't think that it's just a coincidence, as far as I know. So something like alternating between -1 and 1, it doesn't have a limit because it alternates between 1 and -1. Just like if you had, you know, you can think there's an analogy with the x over, sorry, the absolute value of x over x, where you had this -1, 1, and at 0, it had no limit. So this is a powerful concept. And this thing, when we had defined a function, when we had the function's limit, there is a connection, and it says that if f of x has the limit L when x approaches infinity, then if this an is f of n, then the limit of an as n approaches infinity is L. The converse is not necessarily true. Very easily verified. We can come up with a really pathological function which is 0 at all integer points, and then it's let's say it's x in every other point. So this function doesn't have a limit at infinity. It can have infinite large numbers and zeros, and so forth. So this converse is not true. So if a of n's limit is L as n approaches infinity, then it doesn't mean that if you generalize this an equals fn, then that's the limit. It's usually, not necessarily so. It's very important to understand. But this way it's true. If you have the continuous version in some sense of this an function, then if that goes towards some limit L, then obviously the sequence goes as well. Here are some considerations, not going to go in great detail in here. Algebraic limit laws. If we have two sequences, an and bn, and they have limits capital A and capital B, then the limit of a sequence of constant numbers, I mean, if you have just a sequence of the number 5 and it's 5s all over, then the limit is 5. Obviously. If you have the limit of c times an, then it's c times the limit of an. If you have a sequence of a's, sequence of b's, then the limit of the sum of an and bn is in fact the sum of limits a and b, and same for differences. The product, yes, and true. For the an divided by bn, it is the limit of a divided by the limit of b, provided that the limit is non-zero and none of the elements in the sequence of b's is 0. Obviously, because you can't do the division if the divisor is 0. So these limit laws allow us to evaluate many sequences. So the limit of 1 over n as n approaches infinity is 0. The limit of 1 over n to the k is likewise 0. It's just the product of k 1 over n's. All of them 0. So these shouldn't be surprising. These are you know, I would urge you to compare these into this, compare these with the limits in terms of functions. So here are some examples, very quick recap, quickly go through here. This sequence, you can probably see here, this converges because as n goes to infinity, this goes towards 0, right? 3 over n squared goes towards 0, and what is left is 5, so the limit of the sequence is probably 5. The limit of this sequence is probably harder to find, but you know, you can try and see if you can come up with it. You could have the function, and if you have the function versions of these, then we can actually use the limit laws for the functions, and we can find the separate. Well, we can separate them. We can divide by n to the 4, so we get 3. And well, here it is. So we divide by n to the 4, both the numerator and denominator. So we get, in fact, 3 over minus 4, which is minus 3 over 4. And these are all pretty neat, easy to do tricks. 2 to the n over n squared. This goes towards infinity. Is not immediately obvious to see here, but you can use the both go to infinity. You can use a function where you use the L'Hopital rule then, and then the rule that you use there, you find the derivatives of both, then, and you notice that it converges. You can take the derivatives as long as it's infinity over infinity or 0 over 0, then you can just take the derivatives until you get something concrete that is either concrete over infinity, a number over number, number over infinity, in which case it's 0, or it's infinity over a number, in which case it's infinity. So, and then there was this thing 1 plus 4n, 4 over n to the n. Well, that's e to the 4. Which is not fairly, well, it's a bit hard to do. I'm not going to expect you guys to be able to do these kind of limits. I mean, yeah, 1 plus something over x, that to the power of x as x goes to infinity is in fact e to that something. You can go through this example. All right. Let's do one more group work, and that would be 5.3. Consider this sequence, 5n squared plus 1 over e to the n. Determine whether or not this sequence converges. If it does converge, what is the limit? And I'm going to just go out and say that you should use L'Hopital twice. And do that, and it shouldn't take you more than 5 minutes. And we'll have a, look, I'll just move these guys to these rooms. All right, and find the limit of that 5n squared plus 1 over e to the n. For a couple of more minutes. So what did you get here? What was the limit? I know I can see it, you know, without thinking about it, and so will you if you think about it. Yeah, it is 0. In fact, that is 0. Probably had to use L'Hopital twice, and you'd come up with 10 over e to the n, and then you notice that 10 over e to the n still goes to 0 as n goes to 0, right? Yeah, all right, that's fine, that's good. Now, the thing is, the nice thing about a sequence and functions, one other thing is that if you have a sequence that converges to a real number L, and you have a function that is continuous at L, then taking f of an and making that into a sequence, then that converges to f of L. And we could in fact say that this if this limit has a if this sequence f of a n has a limit at f of L, then in fact f is continuous at L. It's if and only if. If we have a convergent series, I mean, we could have this as a definition of continuity. So that if a sequence of numbers such that for all a n, f of a n is defined, then if that sequence f of a n converges to f of L, where L is the limit of that sequence, then f is f is continuous at L. So you could have this both ways. Not so that, and that should be understood in such a way, not just that if one sequence, but if all sequences. So it has to be for all meaning, okay, let me rephrase this. So if we have a sequence and it converges to L and f is continuous function, then f of a n converges to f of L. And the other thing that could be said is that if all sequence, for every sequence that converges to L, such that where f is defined at all values of a n, if for all these sequences f of a n converges to f of L, then f is continuous at L. So it's kind of stronger than just saying that if a sequence converges to L and f is continuous, then the sequence f of a n converges to f of L. There can be a stronger statement said. But still, you know, they're more intimately connected than just this spurious connection that seems to be from here. Well, it doesn't really matter. That's not a big thing about this course, from this course point of view. There is another thing about this, why you can do this. I mean, it allows you to find limits for such that 2n plus 1 over 3n plus 5. If you take the limit of that sequence and then you take the square root of that, and the square root is continuous for around the point. I mean, if you take without the square root, take the limit, then you get 2 over 3. You can verify, but the limit is 2 over 3. I mean, of 2n plus 1 over 3n plus 5. If you take the square root of that, then by applying this theorem 5.3, you know that this sequence converges to the square root of 2 over square root of 3. Last thing that I'm going to say today is that if we have 3 sequences, an, bn, and cn, and if all the numbers in sequence A are smaller than all the numbers in B, which again are smaller than or equal to all the numbers in C, or in other words, if the sequence of B's is between the A sequence and the C sequence for all n, and if both A and C converge to the same number, then B also converges to that number. That's called the squeezing theorem, and this is really powerful later when we look at limits of series, not sequences, but series, meaning that we are adding stuff and making infinite sums. Then this limit sequence, this squeeze theorem for finding the limit of sequences comes in very handy. So that's the last thing that we take. So I'm not going to go through this proof because we're running out of time. You can use the squeeze theorem to find limits of several of these. For instance, we know that the cosine function is between -1 and 1, and we find the limit as -1 over n squared and 1 over n squared, and find that both of them has 0 in the sequence. Minus 1/2 over n, well, we can say that, you know, this this alternates between 1/2n and -1/2n, and then we can squeeze it between minus and then the minus on the outside and the without the minus, 1/2n, and we squeeze this between those, and we find that both have limits at 0 and so forth. So here's the example that you could go through and use it. I urge you to go through this and use the squeeze theorem. It's very powerful. But we're going to stop now, and we'll continue with these sequences and talk about series as well on Friday. We are going to have exercises on the 7th week as well, because I need to have these exercises about, I need you guys to do exercises on these sequences and series. I'm probably not going to put you guys to do the on the last week's exercises. I'm not going to make you do the peer review, so I'm going to probably review them myself, the last week's exercise. So the 6th exercise is the last one that you have to do the peer review on, and then the 7th week exercise I will do the peer review myself. Go to the Moodle page. I'm going to stop now. I'm going to have some practical matters here, so tell you that, well, I can tell it on record, so if someone watches this over. Go to the Moodle page. There's a vote for the timing of the online exam. I couldn't get any reasonable answer about when there are overlapping exams from the exam administration. Maybe I've made a blunder when I designed this course, because I don't know if you know, we've moved into this new SISU system, and it works very differently, and I don't know about the scheduling of the exams, how that works nowadays. Usually what I do is I get an email that tells me when the exam dates are, so that they make sure that there are no overlappings between people who have this as a compulsory and some other course as compulsory course. But I was kind of thinking that it's Thursday, I think was Thursday, yeah, December 10th. That was my suggestion for the date. And it could be morning, midday, or evening exam. Someone said that the evening is bad and asked for the midday exam. So I put these three choices. You can choose more than one, but don't choose the one that you cannot attend, and it will be online. And if there are many people who couldn't attend, then I can arrange another one even before the New Year's, because I mean I want everyone to have a chance to take the exam before the New Year's, because I know that some people need the credits very early next year or something like this. Some people may have things with maybe issues with the immigration. Maybe they are in the country and going to have to leave or get to this their other university, or maybe some people have problems with the Kela thing or something. So I will try to make sure that everyone has the chance to pass this course by latest very early January. All right. I'm going to stop the recording now. If there are any questions,